Good afternoon. Welcome to this session. My name is Maria Vranic. I come from IST Portugal, from University of Lisbon. And it is my pleasure to introduce a session on new particle accelerators. And the main topic today is accelerator on a nanophotonic chip. Okay. So I am going to start this with an anecdote. So the last session also had an anecdote, but this one is different. So I come from laser plasma community, and one of the driving forces of our scientific achievements is having access to very strong pulse lasers that were developed in part thanks to the chirped pulse amplification scheme that was actually awarded a Nobel Prize in Physics in 2018. And when the Nobel Prize winner, Gerard Moreau, was visiting Lisbon and giving his Nobel Prize lecture, he told a story. It was quite remarkable, and it illustrates very well this idea that we cannot really know what is going to be the impact of our research, and it can come really from unexpected situations. So what he told us is that his postdoc was working with a laser in the lab, and he had accidentally removed the goggles in the wrong moment, so he was not wearing the proper protection, and he got a laser into his eye. So, big panic. This is happening in Rochester, US lab, so you can get sued very easily for these kind of things. So they ran into the doctor's office, and the doctor started asking very specific questions about the laser. Say, okay, what is the frequency? What is the duration? What kind of laser is this? So both the professor and the student, the postdoc were like, okay, what's going to happen to the eye? I said, no, the eye is fine. It's going to be okay. So tell me about the laser. So, and then they were like, okay, but why are you so interested about knowing what's the laser that did this damage? Because the damage that did was perfect. So a few days later, that's happening in 1993, a few days later, this doctor is calling them up and saying, okay, we need to start a collaboration because we want to use this for laser surgery. And we are now about a bit more than 2 decades later. We get 10 millions of people per year are doing LASIK surgery for correcting their vision. And this is possible because we have this very precise technology that can make a very precise dent into a material, and cornea in the eye is also a material that you can shape. And just because of this error that happened while they were making an intense laser even more intense, trying to work on amplification to study atoms' behavior at extreme fields. So it was not, they were not even trying to develop a medical technology, and it happened to happen on the side. So it's very difficult for us to predict what's going to be the biggest impact of the technology we're developing. And this really connects to the short-term and long-term strategies that were also mentioned in the previous panel. I think the short term, we're usually overestimating because we're overly optimistic about what we can do, but long term, we are underestimating because we cannot really predict all the areas where some new ideas can be used. So, so this was about the laser, and then one of the other applications of this technology was accelerations. So first, it was accelerations in a plasma. We have 2004, there was a triple Nature publication called the Dream Beam. It was the first time it was shown that a quasi-monoenergetic beam can be obtained just using light and plasma, so sending a light beam through the plasma as a medium to accelerated particles. And this is something that it's the first time that we could start dreaming about having accelerators smaller. And the headlines were, honey, I shrank the synchrotron, big physics gets small, and so on. And it created quite a big excitement, and nowadays there's a whole field that's international that people are working on for acceleration in plasmas using lasers. And now we have a new opportunity, and the new opportunity is to port this laser acceleration to something else. And we are talking about nanophotonic chips today, and Peter will tell you a little bit more about this technology and how we can profit from it to accelerate electrons on a very, very tiny scale and with very, very strong potential for applications. So you can go ahead.
Thank you, Maria. So it sounds that I should hope for an accelerator accident in the lab to drive development of this. Fortunately, the currents are so small that we certainly cannot do any harm. But if we are there, that we can do any damage, I think we're at an interesting point. So let me show you where we stand with nanophotonic-based accelerators and what this is about. And then I really look forward to the discussion. So here you see a structure, and this is a small structure, 80 microns long. Now we have 10 times longer, and I'd like to show you that they are really the direct counterpart of what you probably know of RF accelerators. What you see here is a channel that guides electrons. Electrons are injected here, propagate through these colonnades. In the middle, we shine laser light from the left, and this is then the shrunk accelerator. Let me show you why this is interesting, or why is it interesting in the first place to shrink accelerators. You all know these big machines. This is probably the most recent one to build a light source in Hamburg, 3-kilometer-long accelerator. The international particle physics community is even considering the International Linear Collider to do Higgs spectroscopy. For the famous Higgs particle, you need energies in excess of 1 tera-electron volt. Why then would you build such a long machine? Because all these machines are, after something like 90 years of development, limited to a gradient of 30 million electron volts per meter. What is it? It's as if you apply a voltage of 30 million volts to a plate capacitor, where the plates are a meter apart, and you just allow an electron to propagate from here to here. Then you have acceleration of 30 million volts, and that's an acceleration gradient of 30 mega electron volts. This is a large number. This is 90 years of development, billions of euros spent, and it's an impressive number. Still, if you want to reach 1 TeV of energies, you can do the math. You require a 30-kilometer-long machine, and I find it very impressive that our society supports building these huge and very expensive machines. And still, the question is, can we...
ILC is not funded yet.
Yeah. Thank you for pointing it out. Japan is still courageous discussing it, at least. But what's more interesting from the societal point of view, and maybe also because ILC is not going to be coming into play, we'll see, are these accelerators that you probably all know. Some of you have probably already benefited from these machines. They're L-shaped. They can scan around the body of a patient. Why they're L-shaped? Because there's a 1 meter long accelerator inside. Why is it 1 meter long? Because the doctors need something like 20 mega electron volt electrons here to generate sufficiently energetic radiation to do treatment. And our society is getting older and older, which is why this is a big market that is actually supposed to grow steeply. Cancer treatment is a huge, huge point, and you always need these L-shaped machines with this 1 meter long accelerator. And the question you may ask is, can we make this smaller? Can we shrink this by a factor of 100, for example? And so let's look into what's behind it, and let's see if we can use the same principles to build something much smaller. Standard accelerator basically does the same like this surfer does on a wave. This surfer surfs the wave. And an electron, or a bunch of electrons, and a particle accelerator does nothing but this. The electron serves an electromagnetic wave. So we just, quote unquote, need to generate this wave, or this electromagnetic wave or mode here, to accelerate particles. And you've seen the number before. In research machines, we can reach 3 times the 30 mega electron volts per meter. We can reach up to 100 mega electron volts per meter. Why is that? Because the fields in these microwave accelerators are so large that the surface breaks down and we actually draw electrons all over the place. And that's why this is a very hard limit for conventional accelerators. But what if we go up with the frequency? What if we go from microwaves up to optical? Then you probably know that you can shoot very powerful lasers even through this certainly not very fancy glass that this bottle is made of. You really, if you want to do damage to this glass, you need you need high fields. You need fields of something like 30 billion volts per meter, 30 gigavolts per meter to damage regular glass, nothing special. And it's this factor of 100 where damage kicks in that we want to take advantage of. So we really want to reach a factor of 100 larger gradient. I'm going to show you that we're almost there. And if we can make the gradient larger by a factor of 100, that means you can shrink the machine by a factor of 100. How do you do this? It's exactly the same principle. We need to generate a wave that continuously pushes forward the charged particle. We do this with these nanostructures. Why they're nanostructures? Because the size of these structures needs to be on par with the driving wavelength. So if you go from microwave, right, millimeter, centimeter to millimeter size, to optical, this all has to become smaller, and we can discuss the downsides of this, what it means that you have to go smaller, but let me stress the upsides first. So does it work? Yes, it does. Something like, well, almost 10 years ago, our already back then former collaboration partners at Stanford, the group of Bob Bayer and our group, could show that this works. We showed it with non-relativistic, slow electrons from an electron microscope. In California, they showed it with a relativistic electron beam at a special SLAC facility. It works, and we were extremely lucky that we were invited to build a collaboration, worldwide collaboration. We had it in the last panel. I think it's great. Science should be global. We collected the top players in the world to form a collaboration that we call the Accelerator on a Chip International Program, whose goal is to build a 1 MeV accelerator that small, in a shoebox size. The chip, the actual acceleration chip, can be much smaller, can be on your thumbnail, but of course you need to somehow power it. That's why it should be shoebox sized. And we want to look into new ways of photon generation, so light generation. And we were allowed to collect really top-notch people, light coupling experts, electron source experts, nanostructure fabrication experts, simulations is very important, simulation experts, and also the large facilities to form this 8-chip collaboration, which was generously funded by the Gordon and Betty Moore Foundation. Gordon Moore, the founder of Moore's Law, and he insists that it's Moore and not Moore, I learned. Gordon and Betty Moore, a great philanthropist, still alive. Unfortunately, never got a chance to meet them. And they fund this fantastic foundation, which funded this program with $20 million. I just want to show you where we stand. This is the 8-chip collaboration after Corona here in Tel Aviv. This is Bob Bayer. With who, and I should mention it, we're here in the Leibinger session, of course, you see it. I was fortunate enough to receive the Leibinger Innovation Award, second prize for this accelerator on a chip. Where do we stand in building the accelerator on a chip? We have demonstrated all individual elements that you need. You need acceleration elements, deflection elements. You need to be able to drive the accelerator at different locations. You need to be able to exert the forces to keep the beam together. So we need focusing elements. We have the proper sources. But that's not enough. An accelerator is a nasty beast. You really have to make sure that you not only accelerate, but you also have to confine the beam. It's like pushing marbles with a flat hand. After a while, you don't push any marble anymore because they go left and right, and you only end up with one marble that you're pushing forward. So you also have to collimate the beam, and this is the way that is well known for 50 years from a classical accelerator technology. You accelerate in a section, then you have another section where you collimate, accelerate, and so on. So this way you can confine the beam and at the same time accelerate it. And I'd like to show you that this works. This is the structure that allows this. I don't have time to go into detail, of course, but what's very important are these gaps here. These gaps change the functionality. This, for example, if this is an acceleration structure, then this gap here makes this a confinement or collimation structure, acceleration, confinement, and so on. So this is great to see. What's even better for the future is that our Stanford friends have already shown that you can now power such an accelerator not with light that you shine from outside, but with on-chip driving. So what did they do? They used something called inverse photonics design. It's something really great, pioneered by Jelena Vučković from Stanford and Shano Farm from Stanford, where you use computer technology to come up with structures that you would not come up with just with a piece of paper. You wouldn't sketch it, but these are the structures that are the most efficient acceleration structures. And then they also designed something that we call a grating coupler, so they could couple a free space laser beam onto a chip, so the light is now confined here on this photonic chip, and then this drives the particle acceleration. So we have already integrated driving. It works, really fantastic. Here again, these beautiful structures that are then made in the clean room. Everything is in the structure here, so all the knowledge we have is basically in the shape of these nanostructures. How do they exactly look like? And so we now have already demonstrated that we can drive these accelerated with integrated sources. This is just one example that we've been playing around with a couple of years ago. It's 18 microns long. Actually, these days we play with structures around that are 10 times longer. The stupid thing is, if I show you a micrograph of these structures, you just see something very long, but you don't see the interesting nanostructure features anymore, just because, well, it's now 10 times longer, but the structure size remains the same. So I'm showing you this here, and I just want to show you this is the geometry that we use. Shine laser light from the side, send an electron beam into this colonnade structure here, and then this is accelerated by this laser light. The green part is just a mirror. It just reflects the light so that we use it most efficiently, if you will. Just to show you this on top here, it's not so interesting. We just want to show you some simulation results. This structure is so important because it allows us to confine the electron beam. So in this work, we really showed that the electrons are continuously confined by optical forces. And just to show you that this really works, when we crank up the optical forces, we can also overdo this collimation effect. So for example, this electron with this orange trajectory down here experiences an optical force which drives us back to the center of the channel, which is good, but now the force is too large, so now this electron crashes over here. And so you really have to do everything right, like in a regular accelerator, get the fields right to confine the beam, and now we basically go one step further. As we speak, our Stanford colleagues and us are working on serious acceleration of these electrons in conjunction with collimation. Just to show you that this is something you might have seen, not so sure, when you want to keep electrons together, it's really interesting. There are charged particles. You cannot confine charged particles in free space very easily. You have to use oscillating fields. And here we do something in simulation, but it's really nice because these are simulations we can realize in the experiment, where you see that we allow the electrons to breathe. And you see here that the energy continuously rises. And this breathing and basically, technically speaking, rotation in phase space, how people call, is something you have to allow to the electrons so that you can continuously maintain them and accelerate them. So this is the dream how this should behave. Why? Because we accelerate here, we can run this movie for, I don't know, 2 more minutes or so, and we will see that we can get electrons up to 1 MeV of energy, and we only lose 7% of the particles. That's important. For an accelerator to work, you have to be able to maintain the electrons in the beam, and this works here with realistic parameters. Where do we stand in terms of technology? It's really interesting to realize that we use lasers that are not too different from the ones that power the internet. Right? You know, erbium fiber lasers power the internet. We can use fiber laser technology, very power efficient technology. We use silicon nanostructuring capabilities. This is what you carry around with you in your cell phones. So it's broadly available technology, mature technology, and we just try to basically piggyback on laser technology, nanostructuring capabilities to build new accelerators. And you might wonder, is this the same story like back in the 1930s when accelerator technology took off? Why did it take off in the late 1930s? Because all of a sudden radar klystrons were there, but they were invented for radar. All of a sudden people realized, well, that's a great power source for an accelerator. So even classical accelerators were not really planned as a tool, but resulted from bringing technology together. What's a dream? One little dream device we can think of. put everything on a chip, just have a glass fiber and maybe some, I don't know, low voltage source going onto the chip, have everything on the chip, and just generate, for example, an electron beam that can proximity treat a tumor so that you can do keyhole surgery with an entirely new beam irradiation device. This is probably more science fiction than science yet, but of course we're working on it and we're working towards this here. I have one slide with some technical numbers here. I don't want to go through it now, but if somebody has a question, these numbers should tell you that yes, we can probably really build this within a reasonable amount of time. Let me come to the end by, of course, thanking those who do the fantastic work and by wrapping up. So where do we stand? Nanophotonics-based particle acceleration. I haven't said the word accelerator yet. Nanophotonics-based acceleration is now at a point where we have demonstrated all the important elements we need. We have demonstrated 2 GeV per meter, so that's already more than standard accelerators can reach. We have these on-chip feeding, which will be important for really miniaturization. We have this fantastic new photonics design way, which is called inverse photonics design, that we can use to come up with really fascinating structures. We have this net energy gain. As I said, we're working on it towards really large energy gains, reaching, for example, a mega electron volt. What's interesting, this operates naturally on attosecond timescales. So on extremely fast timescale, 1 attosecond is a billion of a billion second. So we can look into extremely fast processes with these beams, if you will. So that could be an interesting science application. And well, where's this going? Soon we hope to reach a 1 MeV accelerator. It might be interesting because the natural form of the electrons are actually attosecond, if not even zeptosecond short electron pulses, extremely short flashes of electrons. And maybe new light sources might result. And with that, let me just point out this really wonderful movie that the Leibinger Foundation shot about this. I didn't want to put a link here, so just throw in Leibinger Bayer Hommelhoff into YouTube, and you find it. Beautiful 6-minute movie. With that, let me wrap up. Hold on, I wanted to show this last slide. So this is all the beauty of nanophotonics, and we really want to take it to our advantage to build new photonic accelerators. That was kind of the overview. I hope not too long and not too short.
Thank you, Peter. Very good. So I would like to, thank you. I would like to now reinforce one point from your talk. So it was a little bit short in the end. We were discussing potential disruptive potential of this technology, and we came up with already a few applications that are quite important. So you mentioned somewhat in detail the electron therapy for cancer, that maybe can be this, having a microchip that small could really be a game changer. But even currently, just to have the electron therapy that's standardly in the cancer labs already, they really need a big device, right? So shrinking this device to a shoebox size is already a big thing, right? So how far off we are from doing that?
So we're not really talking about a medical device, and I learned that if you want to venture into new medical devices, never underestimate that just building the device is not good enough. You also, of course, need to prove its efficacy and show that it doesn't have really bad effects. So the device itself. And if you want to, where we're discussing replacing current electron beam irradiation devices, right?
Exactly. So that's an easier step.
Right. So there, people often irradiate large areas. You need pretty large currents. This is something. This is really the downside of these narrow channels. That here, so far, we haven't really demonstrated large currents. And this is interesting when you have surgery, your breast is open, and you just want to sterilize everything. For this, for example, you use electron beams. Here we have to work on the currents. But what's interesting to realize is that with these nanotechnologies, we can of course not just have one acceleration channel on a chip, but we can print many next to each other. So this will be interesting. We're looking into this. The theory work is out, but we haven't demonstrated it yet. And in the end, it's only about the average current. So you could also just say, well, let's buy a more expensive laser that doesn't operate, say, at a 100 kilohertz rep rate, but operates at 10 megahertz rep rate. Right away, you have a 100%, factor of 100 current increase. So I think, in terms of timescales, it's really hard to say. Taking it from the university lab to a company, but I don't know. I'd hope 5 years.
Well, that's optimistic, I think.
For the shoebox, not fully integrated.
For the shoebox. Okay, very good. So there is another thing. Many people in our field are quoting that radiation generation is something very important for the future, and we were trying to make new sources of different types of radiation, different frequencies in whatever configuration we can think of, right? So this accelerator on a chip has a good potential to provide electrons for something like a free electron laser that's small, that could be compact. And could you elaborate a little bit on that?
Thank you. This is, I think, very important. You probably know that the European XFEL is an accelerator only built to generate light again. So this is really what accelerators are used for these days, photon generation, light generation, because from electrons you can get any wavelength, basically any temporal structure. What's also really interesting here when you go to the nanoscale is that even the theory for free electron laser radiation is not fully worked out. You're in this what people call the quantum free electron laser radiation regime, and there's still theory papers worked out. So we might even end up in them. I'm really curious to show that we could come up with more efficient ways of photon generation. And there, what's extremely interesting is that, and this is very recent work, with this nanophotonics design, people are now used to generate, talk about nanophotonic bands. This is just for the experts. So in solid state physics, one doesn't really think in the real space domain, but people think in another domain. It's basically the Fourier transform of the real space, again, for the experts. And this is now also has been introduced in nanophotonics, where this is now a big field. And just very recently, it has been shown that you can now structure these nanostructures that you've seen such that an electron radiates up to 100 times, and in the paper they say up to 1 million times more efficient than before. So generating light out of electrons is long known. You probably know the Cherenkov effect or some other effects where an electron...
Synchrotron?
Excuse me?
Synchrotron radiation?
Synchrotron radiation, thank you. Where an electron generates light, but with the nanophotonic structures, you can now use this fantastic design space that you have at your disposal by just shaping these nanostructures in specific ways to make the radiation much more efficient. And this is something that can be a real game changer. So there we have at the very beginning, I'd say, but this can certainly be one of the most interesting medium to long-term perspectives.
Yeah, okay, thank you. So I'm going to open up this for questions from the audience. So the fluffy cube, can we have it, please? So we have a question over there. Yeah.
Hello, thank you for the very interesting talk. So I wonder why you didn't mention the obvious application of particle acceleration for using testing fundamental physics. So what is the problem with this technology? Why we cannot just replace the next version of a linear collider, our traditional technology, with this technology?
Thank you. Fantastic question. So it's really fascinating to see what's inside of these conventional accelerators. I also had to learn this. I'm not an accelerator guy. Until recently, I wasn't. Now I think I am getting one. It's absolutely spectacular to see at which level you can control these high-energy electrons. And when you talk to these experts, then, for example, just what they call the final focusing section of this International Linear Collider is several kilometers long. There you don't accelerate anymore, but you just have to form the beam so that actually the two beams really hit each other at a tiny, tiny point in space. And so for these high-energy physics experiments, so people think about it. There are always workshops about next-generation colliders. It's always about colliding beams, so they call them colliders. And this technology is being considered now. There was a huge breakthrough for us that in a very authoritative review, two accelerator experts now really included considering nanophotonic-based accelerators. But let's put it this way, they think in really long timescales. And of course, it's great to see that, yes, let's consider it, and it might be built in 30, 40, 50 years. But I don't find it too, let's say, interesting to think in such long timescales, because I think there's so many nearer term applications. But it's certainly being considered, and the larger gradient there is of course very interesting. If you can have just a 1 kilometer long tunnel and do Higgs physics experiments, people would definitely love it. So thank you. Yes, I should have mentioned it, that this is certainly now also being considered, but it's really very, very long time scales that there you have to plan and think.
The focusing is this task that is open.
Focusing was just one example. It's really just one example. It's for these machines. It doesn't suffice to just accelerate electrons to a large energy. You also need large currents to look for these very rare events. It took so many years to find, decades, to find the Higgs particle. This was not because the electron couldn't be reached, but it's this what they call the luminosity. How many really head-on events do you have that could generate this Higgs particle? And this directly depends on not only the energy of the electrons, but also the current. This is really impressive what we as global society have reached in terms of conventional accelerators. Still, of course, it makes total sense to also think, can we reach similar goals with other technology? Yes, but it's certainly not straightforward.
Yeah, and I would like to add here for the current, it's current in a very tiny volume. So for conventional accelerators, you need extremely good beam control. And this is something that new technologies usually struggle with a bit. So actually, in that sense, the accelerator on a chip is promising because the beam control that can be achieved is quite good. Okay, so there was another question. Go.
It's here at the moment.
Okay, sorry.
So,
Sorry.
Really great achievements and very nice talk. So as an accelerator guy, I have a few questions on kind of some numbers. So first of all, could you comment basically on the current densities which you reach at the moment? Can you comment on material fatigue? Can you comment on reproducibility of your beam? Do you have some issues with charge up as a function of time? If we think about high energy physics applications, these machines need to run in a stable way over years, right? So
thank you so much. Fantastic points. The accelerator physicists are always the ones that put their finger into where it hurts. Let me start from the back. This is really nice. Reproducibility, material fatigue are no issue. We can work with one structure if you inadvertently don't really crank up the laser power, but let's assume no accidents, but we learned sometimes accidents are good. Without accidents, we can experiment with one structure for months. No problem. So the materials can take it. Charging is interesting. We use doped silicon, so it's slightly conducting. That's sufficient to somehow get rid of charging. That's important. Not all materials have good optical properties and can be slightly conducting. So that's why we still stick with silicon, even though initially we thought, well, we go away from silicon right away just because the Demer threshold is maybe factor 10 smaller than, for example, for silicon carbide. Still, everybody is extremely happy with silicon. That's fascinating to see. And your last question, current densities. You know, as an accelerator physicist, that for every accelerator, everything or all these properties are defined at the source. And we have the same issue because we haven't really invested much into developing new sources. So currently in our experiment, we just use an electron microscope as an electron source. When we laser trigger this, so we just want that an electron arrives when the laser beam also excites the structure. we currently get less than 1 electron per laser pulse into the structure. It could be much, much better if we just build a compact electron source. But when you do this, we had to learn that the hard way. We basically reinvented the electron microscope with slightly different parameter sets, which, and this is also something that everybody has to learn the hard way, charge particle optics is 100 times harder than light optics. And so we resorted to let's just forget about trying to achieve larger current densities. Let's first try and see if this works in the first place with single electrons and try to achieve acceleration. But with actually 1 or 2 people in my group are always working on new sources. And so we hope to soon have 10 electrons accelerated with 1 laser pulse. You still think that's nothing. The nice thing is we can operate at 10, 100 megahertz, and then this is already getting, could be already very interesting currents.
In this direction, maybe one last question. Can you say something about the scalability, the energy scalability?
Thank you, perfect.
If you could scale it up by a factor of 10, you would be in an extremely interesting range, also thinking PET scanners and so on.
Thanks so much, excellent. Scalability is, nature helps us. So once the electrons are fast, the structures actually become larger. The spacing becomes larger because the electrons reach the speed of light. And that it's easier to make these structures. So that's great. And currently we work with 1 millimeter long structures. You probably know that today's chips are manufactured on wafers that are at least this size. So we can currently have at least a factor of 10, if not 100, headway in front of us with standard nanotechnology fully developed for silicon. We can just go to a foundry, tell them, make us an accelerator, whatnot, I don't know, 6 inches, 10, but 12 centimeters long or so. You can just get it within a week. So scalability is already there. The industry is already there. This is really interesting. And then you would have to stage, which just means you would just have to angle, so tune the angle and position wafers next to each other. But this is standard technology. This can be done. So this is really interesting. I think the scalability we get for free because silicon nanofabrication is so advanced. Thank you.
Back to the comparison with the standard accelerator on cavities. How does the energy balance compare when you include everything?
Thank you. Fantastic question as well. There was at SLAC there was the head of accelerator research group, Bob Seaman, an accelerator physicist, and he was exactly looking into this. And there's a great paper out that when you, like in a microwave accelerator, resonate the laser light. So when you reuse the laser light, then you can become as power efficient as microwave accelerators. So you can be in excess of 10% light to electron conversion efficiency with the proper number of electrons. And this brings us back again to the source. So it's always about the source. We need to get many electrons in 1 pulse to become power efficient. And this is also what we're working on. The nice thing is the wall plug to laser efficiency is already there. It's on par with klystrons. You know, fiber lasers can easily be 20, 30, 40% power efficient. So wall plug to optical is there. Optical to electron has already been worked out and can also be efficient. So this is also in principle solved, but again, the devil is in the detail. The source has to become better.
We have another question there. Yeah.
Okay, so it might appear a little bit ignorant, but in theory, you can accelerate, for example, any charged particles. So it's actually divided into 3 different parts. So the first is, can you just do this for ions or any like other positions? And the second is like, if you do an anti-electron where it just be bouncing back and forth. And then if you change it to a neutron particle like an atom or some neutron, where that it be just like separated to different like charged particles.
I'm not so sure if I got your second question. Let me first answer your first one.
Okay.
And first one is, yes, this works for any charged particle. The stupid thing about protons, so for protons it would be very interesting, for ions it would be very interesting, is again the source. We have to get the beam into this very narrow channel that was just 200 nanometers wide. And if you go to, say, I don't know, 10 micron light or so, this channel can be maybe a micron wide or so. Still, you need to get the ions or the protons in there. That means you have to have good sources. And usually for protons and ions, the sources are not so good. So which just means the current is not, that you can accelerate is not so large just because you don't get them into a single channel. That said, with many channels in parallel, this might be, again, no problem. So this works, and we're thinking about it as well. So we also look into proton sources now. And your second question is,
Anti-electrons or like...
You mean positrons?
Yeah.
Yeah, it's a charged particle, same, basically looks, for us, laser people, positron looks exactly like an electron, right? Only that it's offset by half an optical period, which we can't measure anyways. But
you have to synchronize your laser wells and the entry of the positrons,
exactly,
so not to lose them. But
so in principle, should be doable, but you have to have, again, a good positron source. Thank you.
Oh, the final one, neutron. If you put that
neutron, yeah, doesn't work for neutrons. At least, so if it has a dipole moment or so, you could think about it, but certainly not efficient.
Thanks.
Thank you.
any other questions?
Yeah.
Okay, go.
I didn't hear you talk about plain old boring dental x-rays. 100 kV, simple thing. There's potential clinical value to putting the X-ray source in the mouth and having the film on the outside as opposed to the usual reverse.
Yeah.
So, and then, of course, chest X-rays, that kind of stuff.
Also, fantastic point, of course. The stupid thing there is you slam your electrons into whatnot, tungsten cathode or so, and then you hope that it generates Bremsstrahlung photon. The conversion efficiency, again, is so low that you really need, again, large currents. So it always boils down, especially for these applications where you generate the photons, the brute force or the simple way, it really boils down to get the current up. But yeah, there could be something definitely interesting once we have achieved larger currents.
But wait.
Excuse me?
Did you give us a current number? Because
what I gave you was
milliamps.
That's the point, and
yeah.
we are extremely lucky if we achieve 100 picoamps.
Yeah, but actually, in the future, this may be something interesting because so you said you could control laser light and directly initialize it on the chip. So if you have a counter-propagating electrons that have already been accelerated, and then you have a laser, they can directly radiate the X-rays, and then we're talking something better, right?
Simulated Compton scattering. Yes. Or something like that.
Well, Thomson scattering for X-rays.
Yes, yep, absolutely.
So it is something that could be a small FEL, but we're not there yet, right?
Right.
It is, but it is definitely a topic worth exploring because there is another advantage to from this compact accelerator technologies is that we can have very, very small source size. And then it's already being investigated in the labs for phase contrast imaging that is much better than the traditional X-rays because you can record very small variations in densities and you can have a 3D map of what's being imaged, so it's actually much clearer as an image than conventional X-rays that just record phase modification, and here we can. They record just intensity, total intensity modification on the phase. So we can have really full. We should not try to directly replace technologies that are already in place. We should try to see where our technology has its niche where it can do much better than what exists, right? So.
Last comment, I promise. You're getting very fancy. The problem with conventional X-ray imaging is the apparent source size is the resolution. So just by shrinking the apparent source size, you'll get high quality X-ray images of the body. And that, even without the phase contrast, would be a huge step forward.
Mm-hmm. Yeah.
So you can build these very nice nanophotonic structures. Have you thought about other potential applications than accelerators? I mean, you essentially can build devices where you can optically, where you can enact forces on charged particles and optically control. And could you, for example, build traps rather than accelerators or so? Just as an example.
Thank you. Also, a fantastic question. So in a way, this collimation is kind of a 2D trap. So as a guide, that's good, and you can do a lot with this. What's extremely fascinating, and I didn't have time to go into it at all, is that the particle here, when we think about an electron, we just think about a tiny little red, whatnot, ball that propagates down here, right? Turns out it's really a quantum entity. It's a wave function. And there's now a huge field, or it's a growing research field, which coherently couples light and electrons. And what's really interesting there is that we have to think about the electron as being extended in nature, and we can form it. So for example, one electron can look like this. It can have can look like basically 4 electrons ripped apart, but it's still just one electron. And there people think about new ways of imaging. There's new electron imaging modalities. And for all this, you need good coupling of light to the electrons. And that's why these structures are really also highly sought after. So we have a collaboration, for example, with a group of the Technion in Israel, one of the world-leading groups in this coherent light-electron coupling. And right away, we just sent them a structure with the properties they needed. We could see the coupling was so strong that we could see the difference between laser light driving the electrons and thermal light, so more regular conventional light driving the electrons. It looked different. The electron looks different and can actually measure the quantum properties of the light. That was quite fascinating. And these structures lend themselves ideal for these goals. Thank you.
Okay, thank you. Any other questions? Okay, I'm going to ask you one about this. So could you technically change the structure shape in a way that the electrons are guided in some funny trajectories, actually?
You mean around a curve or something?
For example?
And that's a good question. Why did we never think about this? I'd say I'm pretty sure we could. So we showed deflection. It's really an interesting question. We never build a curve usually. So we have another experiment where it's always about building curves, just to demonstrate, yes, it works. We can build a curve. Here we've never done it. I'm pretty sure we could, but like, I'm blanking. It's always it's a great suggestion. We'll do it jointly.
Yeah. So like I'm thinking of if creating a spiral could give also other properties to the light source. So
sorry, I think that's possible. So on this. In a straight path, somehow doing something to the electrons in addition to somehow guiding it, I think that we have thought about and should be possible. It's fascinating what you can do with these structures, because then you can come up with any kind of very complex near field shape, and it's the near field that controls the electrons. And I'm pretty sure this is doable. You basically again go back and have to probably improve your nanotechnology, your fabrication capabilities, to I don't know, for example, also vary the height or something of the structures. And then yes, I think this should be doable.
Okay. Thank you very much for being here. Thank you, Peter. Also.
Thank you very much. Thank you so much.
Thank you.
Thank you.